Hello, this is the second video in the Game Theory series for OCR Discrete Further Maths. We will be considering the concepts of stable solutions and dominance arguments. Let's compare two examples that we've already seen in the previous video. As you will remember, the row minimums -2, -1 and -2, with the row maximin as -1. The maximums were 3, 4 and 2, with the column minimax being the 2. For the second example, we had row minimums of -1, -2 and -2, and column maximums of -1, 2 and 3. Therefore, the row maximin was -1, and the column minimax was also -1. If the game is stable, there is a saddle point giving the game's value that, for a zero-sum game, must be 0. We say that a stable solution exists if, and only if, the row maximin equals the column minimax. So therefore, in the first example, there was no stable solution, but for the second example, there was a stable solution. What was the impact of that? Well, in the first game, if player 1 knew that player 2 would always play safe, i.e. strategy Z, then they might have considered playing R at times instead of their safe strategy of Q. Whereas in the second game, even if player 1 knew that player 2 would play their safe strategy of X, they would still have continued to play their safe strategy of P. The stable solution for this game is for player 1 to play strategy P and for player 2 to play strategy X. When a stable solution exists, it is in the interests of both players to play safe. The payoff from the strategies is the value of the game. In this case, the value of the game to player 1 was to lose a point and to player 2 to gain a point. For some games, a dominance argument may be used to reduce the options a player may sensibly consider. Let's look at this matrix from Sunil's perspective. Sunil and Linda are playing a game with this payoff matrix, and we want to know what advice we might give Sunil. If Sunil plays strategy P, then if Linda plays X, she will lose 3 points, but if Linda plays Y, she will gain 2 points. If she plays strategy Q, if Linda plays X, she will gain 3 points, and if Linda plays Y, she'll only gain 1 point. The strategy R, if Linda plays X, she'll gain 2 points, but if Linda plays Y, she'll lose 2 points. If we compare Q and R, we can see that 3 is always better than 2 and 1 will always be better than -2. Therefore, we would say that Q dominated R, and there would be little point in Sunil ever playing strategy R. So, if Sunil is never going to play strategy R, in this case the game can be reduced from a 3x2 game to a 2x2 game, and the payoff matrix would now look like this. Let's examine this dominance argument reduction further. If outcomes for a particular row are always smaller than the corresponding outcomes for another row, then the first player will not choose the option with the smaller outcomes, regardless of the other player's strategy. So therefore a row can be ignored or deleted from the table, thus reducing the matrix size and reducing a player's choices from, for example, 3 to 2. Similarly, if the outcomes for a particular column are always larger than the corresponding outcomes for another column, then the second player will not choose the option with the larger outcomes, regardless of the first player's strategy. So a column can be ignored and deleted from the table. again reducing the matrix size and reducing the second player's choices from say 3 to 2. Overall then, better options dominate. Looking at a second example. In this game, which strategy should Joan never play? Well, Joan is player 1. So, looking at the matrix and comparing the rows, we see that if Joan plays Q, she would gain 3 rather than losing 2, or gain 4 rather than losing 5, or gain 6 rather than only 1. Therefore, by comparing the rows, we can see that in this particular case, Q dominates P, and therefore Joan should never play strategy P. If we were to ask which strategy Ellie, the second player, should never play, again this time we'll be comparing the columns, remembering that we're looking for larger numbers because the payoff matrix is written from Joan's point of view. So, comparing columns X and Y, although 4 is greater than 3, minus 1 is not greater than 5. So therefore we can't really sensibly compare columns X and Y. However, if we compare columns Y and Z, we can see that 1 is always going to be greater than minus 5, 6 greater than 4, and 2 greater than minus 1. And therefore, we really don't want this column Z, or strategy Z, because remembering that those are Joan's winnings and Ellie's losses, should never play strategy Z, because it is dominated by strategy Y. If we consider whether there's a stable solution for the game, then let's have a look at the row minimums and the column maximums. We can see that the maximin and the minimax are not the same, and therefore there is no stable solution to this game. Remembering that a zero-sum game has a stable solution if and only if the value of the game to first player plus the value of the game to the second player is 0, and that if the row maximin is not equal to the column minimax, there is no stable solution. And then this tells you that the players should play a mixed strategy, i.e. vary their choices, as both might profit from not playing safe. Identifying these strategies is the central method in game theory. And in the next video, 1.3, we will see how to find optimal mixed strategies.